3 horsepower peak. Bull fucking shit. Gentlemen, welcome back to the shop. We got El Blendtec. Will it blend? Blendtec. We're going to get it back together and test it in a suitably destructive manner. First, old business. Now the comments on these are awesome because there's some experts here that come into the shop to have a laugh with us. And you know, everybody's got their expertise. So it's awesome when we can agglomerate a whole bunch of technical knowledge into one spot here on this here channel. Check it out. These are actually not cracks in the mold. They're called welded lines. And that's what happens when essentially they run the parts too fast through the press. The plastic solidifies and then welds back together right here, and you get a line. Also, some commenters have mentioned that it's real tough to get this right, to eliminate that. It's mainly, well, you start with the design of the molding, or rather you start with the design of the die to eliminate these mold lines. But you can slow down the process, you can change the heat inputs, and you can also, sometimes it's just moisture in the raw pellets, in the raw plastic pellets that causes this. So one guy was saying they went through a hell of a time. They ended up needing to preheat the pellets to drive off the moisture and then keep it covered so that no moisture would go in there and make these weld lines. And then of course successfully added a header here so we could stick an Arduino on here and make this a haunted housewarming gift. Now unfortunately the video, I'm not a videographer by any means, and the video didn't work out because it's not good in low light, and the camera that is, so technically I couldn't get it to do what I wanted to do to show the project. However, I did take some still frames and there'd be an instruction thing on Instructables on how to do that. But essentially, yeah, it's a haunted Blendtec. And this was pretty funny. Check this out. On the board here, earth, earth, neutral. Come on. And then this guy, this SP1, speaker 1. So it's a little buzzer, beep, 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 or whatever, so that you know when the thing's on. It's, you know, in case you didn't see the blades turning and the rumble, the beep would alert you that the thing is on. Now, this is the over temp device here, and just put the old industrial hair dryer on her, what for heating her up. Oh, there you can see. Now it's cooling down. It was hot, it's cooling down, and the resistance is going up. If you want to bypass this, so it doesn't shut off on you all the time, instead you just use your sniffer to make sure it's not getting too hot. You can just unplug this off the board. Might be a good way to get an insurance claim too. Burn your house right down to the ground. I ain't saying. Just saying. So I was kicking around ideas as to what I should actually crush in this thing, because you don't know if those guys on the internet are telling the truth or not. I mean, who knows if the things are actually lasting while it's crushing iPhones and whatnot. So if you've watched this channel for any amount of time, you know that I have a budding case, well, full-fledged case of gold fever. It's a thing. So I go mineral prospecting and whatnot just for shits and giggles. But there's really no small-scale pilot-sized crusher. I figure, what the hell? We're going to try and crush some gold ore. Get the gold out of her. And this is interesting because this all ties in with another project where I took a UV laser to test the efficacy of cheap sunglasses. And yes, they work great. However, I also discovered that when you flash a UV laser at quartz, now quartz is the good stuff, it's the stuff that contains the gold for the most part, it flashes differently than a plain old rock. Okay, so that's no big deal because you still got to find these. However, if you've watched Yukon Gold or the Hoffmans there, you know that a placer mine is gravel. They take gravel and they essentially just wash the gravel and then get rid of the quartz. This goes off into the tailings because it's not worth it to crush everything up. However, if you had a way to sort the quartz, the gold-bearing quartz, out from the other rocks, then you could only crush this and get even more gold out. So as a sideline project, I've been making something that actually sorts the good rocks from the bad rocks. And now that we've got the good rocks, we need to crush them to get the gold out. All right, we're back down in the Empire of Dirt here. I left off the basal platen, and you can see we have an additional little red wire. What that is for monitoring with the oscilloscope, monitoring the commutation noise so that we can determine the speed of the motor. This is maybe not for home gamers because it's got 120 volts worth of pixies. Might melt your fillings if you stick it to your tongue or whatever. No accounting for some kids, you know what I'm saying? So we get on to this. This is the receptacle. Now you look at this and you tell yourself, plastic, garbage, it should be glass. Actually, no, this is polycarbonate, super tough material. In future videos, maybe in a couple weeks, I'll show you just how tough. I got something planned. But yeah, this is a good option because it's a lot less brittle than glass. So the glass might be strong, but it'll fail on you when you least expect it, and then thermal shock, this and that. This plastic doesn't have any of that problem. This is expensive. Polycarbonate is an expensive plastic. One thing I don't like about this is the built-in bearing here. There's just the one bearing, and it is impossible to seal a rotating element from water ingress. There is going to be moisture that comes, even if it's not droplets of moisture, there's still going to be moisture that collects just through osmosis into this bearing. This is going to be your failure mode here, but I have heard that they're pretty good at warrantying these. They know that's the failure mode, and they'll scoot you one of these out if it does fail prematurely. And this is interesting, the shaft, non-magnetic, stainless, and the blades also non-magnetic stainless. That's probably a 304, something like that. Okay, we are gonna have some dorkly fun. We got our nerd test gear out, what for testifying this thing. I had a peek at the box here. 3 horsepower peak. Bull fucking shit. And I will tell you why that is complete and utter marketing wank nonsense. They think we're fucking stupid. Now, I might have been born in the dark, but I wasn't born last night. Out of the wall, you can only get 15 amperes worth of pixies at 120 volts. 15 times 120 is 1800. Now, you got to root mean square that, yada yada yada, multiply it by 0.7. So that gives us 1200 and change. 1260. That gives us 1260 watts. Maximum we can get out of the wall without the fuse blowing. Now, watts. Who the fuck knows what a watt is? Well, 747 watts to the horsepower. So, 1260, remember that number, divided by 747, remember that number, is 1.5, 1.6, between 1.6 and 1.7 horsepower. That's max. And frankly speaking, if you were that close to the line, you would blow the fuse. So, now we know the numbers don't add up, but we can also check to make sure that the actual test results don't add up and that they're lying right through their teeth to us. But anyway, you don't have to take my word for it, because I'm going to show you. And the way I'm going to do that is with this little device that I cobbled up. It measures watts and volt amps, apparent power, as well as cos phi, which is the power factor. The power factor is how much the current lags the voltage. Not to get overly complicated, but this little device is like X-ray vision for electricity. It tells us exactly how much power this thing is pulling. And also, for shits and giggles, we're gonna pull out the thrillimoscope. What for seeing what the pixie dance looks like while this thing chooches. Well, we'll just go ahead and arm this And uh-oh. Ladies and gentlemen, we have a problem. This never happens. There's a switch back here. Yeah, duh. Gotta turn that on. There we go. Blendtec. Haha. And you can smell the brushes are burning. They're seated in there. Obviously, in the last video I showed you, they weren't seated in at all. There we go. We're on. We're gonna go low and see what happens. We're in watts on the top scale. Okay, so at low speed, it's running around 60 watts, about what a light bulb would. It's drawing 1.5 amps, 123 volts coming out of the wall. And you can see here the PID, the control algorithm to get the speed steady is it's kind of the San Francisco type of style, hunt and pecker. It's not a PID where it's actually seeing where it bumps up to and then smoothing that out. It's just up and down, sort of like a thermostat. So if we see here we got the current transformer. This is the amperage going into the motor. Oh, it timed out. It times out there. Oh, that was interesting. Okay, let's stop. So what we're going to see is we're going to get a whole bunch of current to get this thing up to speed, and then it's going to overshoot, and then it'll come back down. Overshoot, yeah. And you can even hear that. So that's the voltage on the brushes. It's being clipped. That AC waveform is being clipped. We go up to medium. Yeah, same thing. Overshoot. Now it's looking quite a bit more sinusoidal. We go up to high. You can see our current transformer is saturated, so I'll have to change the burden resistor. But that's the voltage at the brush being clipped. And at high speed here, we're running at, well, it's all over the place, but say 175 watts. You can even hear it hunting. It goes way up and then comes way down. And if we watch the control here, oh, for fuck's sakes with the stopping, you can see the control here is actually hunting. Watch this. Yeah. Hey, we're going to take a new direction, an intermission. I'd like to introduce you to a mountain of a man and a YouTube machining legend. I mean, he's right up there with Mr. P22222 in my books. And the interesting thing about this is he makes a living as a job shop machinist. So he gets up to some real interesting stuff in the shop. Here's some spray metal transfer. This is for building up shafts. This is quite a common procedure in heavy industry, but likely you've never seen it before, and he brings you into his shop to show you this.
Okay, we're going to do our bond coat.
Also, a lot of guys have been asking me to do more hydraulic videos. He's got some basic hydraulic troubleshooting videos, good to watch. Also, you young fart smellers that are maybe interested in getting into a technical trade, you're going to want to check out his channel because he is a job shop machinist. You can see what the day-to-day entails. I will tell you, in my opinion, you know, there's a lot of old guys retiring a technical trade. You can make a lot of money as a tradesman. And most of the time, despite what the universities will tell you, you will make more on the tools than you will sitting at a desk being an engineer. It's the sad truth. And why is that? Supply and demand. Nobody wants to get dirty anymore. Also, university schools, they don't make any money if you're on an apprenticeship. You get paid to learn. You're 4 years before you become a journeyman. Whereas you go to university for 4 or 5 years to get an engineering degree, you're coming out of there with 100, 125 grand worth of student debt. After 4 years, you come out with a journeyman machinist, or millwright, or welder, or heavy-duty mechanic, or instrumentation mechanic, or electrician. Any of those heavy industrial trades, you have zero debt and you're making more than an engineer out of school. But I digress. I really enjoy watching his videos, especially because you get to look over the shoulder of a master. Just watching him work, you pick up little habits that you can't pick up from a book. So you'll watch a 40-minute video and there'll be 4 or 5 things that are like, holy shit, that's the smartest thing I've ever seen. So go and check out his vids. There's a link up in the corner as well as a link in the Choochily Chew. Go over there and check them out. For God's sakes, don't tell him I sent you. Okay, we're going to do something interesting here. We got it on watts. We cycle through to apparent power. And now we're going to go cos phi, which is the offset between the voltage coming in. Remember, this is sinusoidal. It's an AC waveform. And the current. Now, in industrial applications, you want those to be as close to as possible because the power company dings you if you're too far off. So we'll put her in low here. And normally on a motor we would see like 0.75 under no load. Now under load that's going to go up, but this is just brutal. That's terrible. Not that it really matters for something like this, but it is terrible, just to let you know. Now we'll put it up to medium and you'll see that jump right up. Now we'll put it up to high. And then we're actually, it's actually somewhere in the vicinity of not completely horrible. You see, no load has gone 2.1 amps. Okay, so let's go over here. Let's go over here. We're going to turn off channel 1. We're going to bring up channel 2. We'll change the trigger a little bit. Then we'll zoom in on the time scale. Okay, there we go. We'll take a single shot of that. Now we're going to move that over. Well, I measured it, but I had to get the calculator out here because this 1.77 kilohertz divided by 4 waveforms, yada yada yada. It only ends up giving us, what was it, 2200 ripms. Now, this says it runs at 28,000 ripms in high. However, have a listen. Yeah, I know, right? Not even close to high enough pitch for 28,000 ripms. Now I'm going to do what amounts to a little bit of fancy footwork here, but it's just a tool and we all have it. We're going to use the confuser. I'm changing the sound of the blender into a WAV file, and then I'm putting it into a free piece of software, Audacity, which is for audio files to mess around with sound clips. However, it allows us to FFT, fast Fourier transform. That is a tool. Don't let the $1 million word get in the way of that. It's just a tool. So we're going to analyze this. First we'll filter it a little bit and then we'll analyze it. We'll see where the loud spots are. Those are the frequencies that are loudest, and from that we can determine quite a bit. So here we have a peak at 30 Hertz, which equates to about 1800 RPM. So that could be some bearing noise, or it could just be a rattle in the machine itself. That's maybe the resonant frequency of the casting rattling around. The next peak here is 120 Hertz, which is 7200 RPM. That could also be bearing noise. It could be a resonant frequency node of the entire system. Then we have another node at 313 roughly. That equates to 18,780 RPM. I'm going to go ahead and bet dollars to donuts that despite what it sounds like, if indeed it is running at that speed, it sure is quiet for such a big motor. Okay, so what we're going to do is we're going to use an optical tachometer, and it sends out a beam here of red light, and when it bounces back off of here, it clicks it, basically makes it click, and it counts up to how many RPM it is. Okay, even though we've checked the speed optically, I'm going to do this the sketchy way, just for shits. We got it all set up, just for shits and giggles. However, now that I know that it turns at nearly 20,000 ripms, I'm a little bit sketched out. If yeah, I don't want this coming out like a bullet. But we will check it in low speed. What's going to happen is that magnet is going to wipe past that inductor. It's going to create a voltage spike that we should be able to pick up on the O-scope here, and then determine the speed of the thing that way. There we are. Right now I got two waveforms on the screen here. We're going to go from one to the next. So we can see here it's showing us it's 70 hertz. 70, well, 7 times 6 is 42, so that's 42 zeros, 4200 ripoms. Now let's see if that coincides with what we get optically, just for shits and giggles. It's all over the place. I guess it doesn't need to be that accurate, but we have 37, yeah, 42. There we go. Confirmed it. Okay, this next part's going to get a little sketchy, so we'll put the old, my precious oscilloscope away. But we are going to have this guy up. We already know that the horsepower is bullshit because the math doesn't add up. And we had a look at it there under no load. We also know that the max RPM is bullshit because we looked at it. We know for a fact it's 30% less than what it should be. What are we going to do? We're going to crush up some gold ore. What for getting the gold out? This should be a nice hot supper for it. Oh, I just moved this over. Look at this. Ugh. That is why they put this plastic fish paper on there. Look at the brushes. I was going to load them up one at a time, but ain't nobody got time for that. Why does that not go on? Well, what we have here is a clear and utter failure to chooch. Motherfucker. Can't believe everything you see on the internet. Apparently you put hard stuff in there. She shears the pin right off. Let's have a look at this, see what went wrong. Okay, we're going to ease her in a little better this time. And you're going to want to go ahead and light a smoke. I'm quite sure you can get silicosis from over the internet. And that's what quartz is, silica. You'll also need your safety squints. Possibly ear protection. Might as well double up on the condoms while you're at it. Jesus. Keeping in the silica, so we're going to add a little water to the mix. Unfortunately, it's not quite winter yet, so the tap water is tough to come by. Comes in bricks here in Canada. We're going to use the holy water. Avoid skin contact. Okay, well, it seemed to be working okay, but she done give up the ghost again. I was getting a fair hot supper, I would say. Let's have a look here. Oh, she's toasty. Roasty toasty. Oh, that's not good. And the control board fell out, but that's likely my fault because I didn't put the bottom in. I'll put the bottom in from now on. Okay, we tightened that up once again for the second time, and surprisingly that polycarbonate is tough as shit, eh? It's way better than glass in this application. crushing the rocks. As you can see, it's not doing tea-bag. So I keep tightening that. It loosens off, breaks off. As you can see though, crushing rocks, that's about as hard as it's going to get. It's drawing 1,300 watts, which is way more actually than, that's surprisingly powerful. That's far more than I would have thought. Well, despite being reasonably skookum and surprisingly more powerful than I thought, it still cannot make a rock smoothie. Now, I don't normally do this, but there are some rabid blender people out there who want to know what my opinion on this thing is. Okay, so in its totality, the motor is pretty skookum, even though it's ugly. I mean, it's got lots of power. However, having said that, the thing is $400, $500. Is it worth it? I mean, I like pina colada, but I don't have that many pina coladas. You know what I'm saying? It's a blender. $500, people. Get your head out of your ass. Well, thanks a lot for watching. Keep your stick on the ice. Almost forgot the most important part. We find any gold? You're darn tootin'. Quarter penny's worth right there.